easier to stabilize. In the DCM mode, it's easier to stabilize. The peak currents are going to be higher in this mode. So the disadvantage is that because the peak currents are higher, the conduction loss is higher. You remember that we had conduction losses and switching losses. So we said that the switching losses are going to be smaller, but the conduction losses are going to be higher. So we need to have a larger core because of that. So it's mainly suitable for low power application, let's say around like 75 watts. Otherwise, it's not going to be a good choice. But see that like most of the chargers are now having a flyback converter. So one last thing I wanted to do, again if I can find my notes, is to show you the relationship between input and output in the DCM mode of operation. Maybe I can also mention some more advantages of DCM. Advantage of DCM is that you can use a slower diodes, and you don't need much filtering. Okay, so in the DCM mode, if we want to calculate the relationship between input voltage and output voltage, right, we can't use the volt-second balance anymore because now we have 3 times. It's not that easy to use the same method that we used before in the CCM mode. So as I mentioned, like we use P in is equal to P out, right? So if we use that, basically our P in, it's gonna be Li squared divided by 2 times switching. This is the energy stored in the inductor. It's in the magnetizing inductor, right? We have the F switching. We also calculated I peak earlier on, so I showed you how to calculate the I that goes through the magnetizing inductance. So that's going to be Lm divided by 2 times dt times V in divided by Lm squared times Fs, right? This is I peak squared. And P out, it's just going to be VO squared over R. So if we make these two equal, we find this relationship between V out and V in. V out over V in, it's going to be d root of R by 2 Lm Fs. So it's very interesting that in this case there's no N, right? So in the DCM mode there's no N, doesn't have an impact on it. If we want to so there's always like some balance here, like about making this T on or dt, can we make it bigger or smaller? Okay, so first of all, if D is bigger than 0.5 or D is less than 0.5, this is the point that it changes from buck to boost, right? So this is something you have to consider. But also something that you have to know is that if you want to reduce the RMS current, we have to make the D bigger. At the same time, if we wanna reduce the switching voltage, we have to make it smaller. We have to make T off longer. So it's always a compromise. So it's something that you have to consider. So the as I mentioned here, like the advantage of DCM and CCM, one of them has better conduction losses, one of them has better switching losses. So that's but basically for each problem you have to analyze which mode is going to be more beneficial. I'm sorry if I was a little bit too over the place. I tried to cover flyback converter, like different concepts about flyback converter, both CCM and DCM. One important part that I want everyone to remember is like that this is basically a coupled inductor. It's not just an isolation transformer. It has like the relationship that we talked about, N1 V1 N2 V2, but am I right? No, V2 over V1 is equal to N2 over N1, but remember that current only goes through one of the cores at each time. So here, like, we store the energy inside the coupled inductor, then when we have a break into the primary current, the energy gets released in the secondary side. Okay, so this is a very famous DC-DC converter. It's very popular in low voltage, in low power applications, also like in some semi-high high voltage applications, because of its isolation transformer. So that was it for today. Thank you so much. And again, sorry I was all over the place, and sorry about my cats making a mess when I was playing. So maybe as a bye, I just like show you my cat here. This was the guy who was making the mess. Thank you.